Welcome to this lecture on neuroimaging for disease diagnosis. Imagine trying to figure out what is wrong with a complex car engine without ever being allowed to open the hood. For centuries, doctors had to do exactly this with the human brain. Today, we will explore how modern technology allows us to see inside the brain without making a single cut. Now that we understand the challenge of studying the brain, let us look at how we solve it. Neuroimaging acts like a magical pair of X-ray glasses. It refers to a set of advanced, non-invasive clinical techniques used to visualize the structure, function, and pharmacology of the nervous system. Before these technologies existed, diagnosing brain disorders was largely a guessing game that often required dangerous exploratory surgery. Today, neuroimaging is the absolute backbone of modern neurology and psychiatry, saving countless lives every single day by revealing exactly where a disease is hiding. Building on that foundation, let us examine the first of our three primary imaging modalities, the CT scan. A CT scan uses multiple X-ray projections to create detailed cross-sectional images of the brain. This technique is incredibly fast and highly sensitive to dense materials like bone and fresh blood. If a patient arrives at the emergency room with a suspected stroke or severe head trauma, a rapid CT scan immediately tells doctors if there is bleeding in the brain. This rapid detection dictates immediate life-saving treatment, making CT the go-to choice for neurological emergencies. While CT is great for emergencies, what if we need to see soft tissue in high detail? This brings us to magnetic resonance imaging, or MRI. Instead of X-rays, MRI utilizes strong magnetic fields and radio waves to align hydrogen protons naturally present in the water of our bodies. This provides incredibly high-resolution images of soft tissues, allowing us to clearly distinguish between white and gray matter in the brain. For chronic conditions like Parkinson's or Alzheimer's disease, MRI scans allow physicians to track the physical shrinking of specific brain regions over time with unparalleled detail. We have seen how to capture the brain's structure, but how do we observe its actual function? That is where positron emission tomography, or PET scans, come in. PET scans are functional imaging tools that detect gamma rays emitted by a radioactive tracer injected into the bloodstream. Because these tracers often mimic glucose, they allow doctors to measure cellular metabolism in real time. This means we can identify neurodegenerative diseases at a molecular level, spotting the buildup of toxic proteins or metabolic decline long before major structural damage occurs and becomes visible on an MRI. Now that we know what an MRI does, let us dive into the physics of how it actually works. To truly understand how an MRI machine creates such beautiful images without harmful radiation, we have to look at hydrogen protons. The human brain is mostly made of water, meaning it is full of hydrogen atoms. When a patient is placed inside the strong magnetic field of an MRI machine, these tiny hydrogen protons align with the field. They then begin to spin, or precess, like a wobbly top at a very specific frequency. This spinning behavior we just discussed is governed by a fundamental rule of physics known as the Larmor equation. Conceptually, this formula tells us that the frequency at which protons spin is directly proportional to the strength of the magnetic field they are in. Omega 0 represents the Larmor frequency, which is the speed of the proton's wobble, measured in megahertz. Gamma is the gyromagnetic ratio, a constant specific to the nucleus, which is about 42.58 megahertz per Tesla for hydrogen. Finally, B0 is the strength of the main magnetic field, measured in Tesla. If the magnetic field strength increases, the spinning frequency also increases proportionally. Let us apply the Larmor equation to a real clinical scenario. A hospital installs a new MRI machine with a main magnetic field strength of 3.0 Tesla. We know the gyromagnetic ratio for hydrogen is 42.58 megahertz per Tesla. We are asked to find the specific radio frequency the machine must emit to resonate with these protons. We choose the Larmor equation because it directly links magnetic field strength to resonance frequency. By substituting our known values, we simply multiply 42.58 by 3.0. The units of Tesla cancel out, leaving us with a final answer of 127.74 megahertz. Physically, this means the machine must broadcast at exactly this frequency to successfully interact with the patient's brain. Moving from the magnetic resonance of MRI, let us look at the mathematics behind PET scans. PET scans rely entirely on the continuous radioactive decay of tracers to emit signals that the scanner's detectors can pick up. A common tracer is FDG, which acts like glucose in the brain. Because it is radioactive, it has a specific half-life, meaning the amount of active tracer is constantly decreasing over time. Medical technicians must carefully calculate how much radioactivity will remain in the patient's brain after a waiting period to ensure the signal is still strong enough for imaging. To predict the amount of tracer left, we use the standard exponential decay formula. Conceptually, this equation models how a substance reduces continuously over time based on its unique decay rate. N of T represents the amount of radioactivity remaining at a given time. N0 is the initial dose administered to the patient. The mathematical constant E represents the base of the natural logarithm, fundamental to continuous decay in nature. Lambda is the specific decay constant for the tracer, and T is the time elapsed. As time increases, the negative exponent grows, meaning the remaining active tracer decreases exponentially. Let us see this decay formula in action with a patient undergoing a PET scan for suspected Alzheimer's disease. We are given an initial dose of 400 megabecquerels, a decay constant of 0.0063 per minute, and a waiting period of 60 minutes. We need to find the remaining radioactivity. We use the exponential decay formula to model this continuous loss. First, we substitute our values into the equation. We multiply the decay constant by the 60 minutes elapsed to get a total negative exponent of negative 0.378. Calculating the exponential and multiplying by the initial dose gives us approximately 274 megabecquerels. Physically, this confirms the clinical team still has a strong enough signal to capture high-quality functional images of the brain's glucose metabolism brain. Having explored the physics and mathematics, let us visually compare these three powerful tools. On the screen, you see three distinct cross-sectional images of the human brain. On the far left, the CT scan uses X-rays to clearly highlight a dark region, representing a hemorrhage or bleeding. In the middle, the MRI utilizes magnetic fields to provide a beautifully detailed, high-contrast view of the brain's structural anatomy, clearly separating white and gray matter. Finally, on the right, the PET scan uses a radioactive tracer to display a vibrant heat map of glucose metabolism, where warmer colors indicate high cellular activity. Together, these images show how each modality offers a unique and vital perspective on brain health. We have covered a lot of ground today, so let us review the most important ideas. First, Neuroimaging has revolutionized medicine by allowing us to diagnose nervous system diseases without invasive surgery. Second, each modality serves a specific purpose. CT scans provide rapid structural images, ideal for emergencies, while MRI offers unparalleled detail of soft tissues using magnetic fields and the principles of the Larmor equation. Finally, PET scans reveal the actual metabolic function of the brain using radioactive tracers, allowing us to detect diseases at the cellular level. You now understand the fundamental physics and clinical applications that make modern neuroimaging possible.